Okay. Good morning. Today we have lecture number 4, and this lecture number 4 and number 5 will be very much connected because we are going to discuss properties of metals. Namely, today we discuss the electric function. I do all necessary calculations to derive the electric function of metals, and on Wednesday we are going to discuss properties of this dielectric function. For example, why metals are shiny, what is Coulomb screening, what is screen potential, what are collective excitations associated with the fluctuation of the charge density, namely plasmons. But in order to do it on Wednesday, I need to do some lengthy derivation. And this is what we are going to do today. So I already said that on Friday we will have a tutorial, so please collect all your questions till Friday. Before I start, let's welcome Rolanda, who arrived on Saturday. Now we are all together in the nice ICTP campus, and let's hope that we will be able to meet in person relatively soon. Okay? I start. You hear me well?
Yeah, I hear you. Thanks.
Okay.
Thanks for the introduction.
The video is okay, because I keep reporting the problem with videos to the computer section, and I keep asking about lectures to be put online. So, as far as I understand, it is not yet done, but again, I hope it will be done soon. And unfortunately, I don't have control on uploading lectures online. Okay, lecture number 4. So, it's dielectric function. By the way, in what I'm going to do today, almost everything is classical, contrast to previous lecture when we discussed magnetism, which is totally quantum phenomena. However, for some part of the lecture, I will keep the Planck constant in my equation, but when the equation becomes too lengthy, I will say when I drop the Planck constant. But we start to discuss electrodynamics of metals, and I'm going to start with Maxwell Equations. Okay? So, since it's electrodynamics, I'm going to use those two equations which are related to electric field. There are two kinds of functions describing behavior of electric field. So one is related to the total density of charges. So, and the Maxwell equation. It's electrostatics. Again, I don't discuss any currents. So nabla E is 4 pi E. And we have a total density of the charges. Of course, E is a function of R and T, and density is a function of R and T. And I deliberately separated the density of particles and charge such a way that density of charge is E, charge of the electron times density of particles. So there is electric field E associated with the total density of charges, and there is electric field D, R, T, which is associated with external charges added to the system. So you add external charges, you have some induced charges. This is, for example, how dielectrics are organized. So this is 4 pi E times density of external charges, RT. So this is a pair of Maxwell equations I'm going to use in order to define and derive some function which is very important for description of the properties of metals. So first of all, I'm going to make a Fourier transform of both of these functions. So I'm defining the Fourier transform as E as a function of RT. This is a vector, is equal to integral over dq over 2 pi cubed. I'm dealing with three-dimensional electrostatics, integral over d omega over 2 pi E, the function of q and omega, e to the power I qr minus omega t. And the same way I define the Fourier transform for the function d, the function of dq over 2 pi cube, integral over d omega over 2 pi d q omega e to the I q r minus omega t. The Fourier transform is very helpful because I plug it into the differential equations, which are Maxwell equations. So these are Maxwell equations. And as a result, I will transform this differential equation to algebraic equations. So, let me consider longitudinal response. Namely, I will be dealing with a part of these functions which are parallel to the momentum. So, I will consider E parallel, which is parallel to Q.
There is something in the chat I think we need to see. Maha said she cannot see the screen.
Does everybody see the screen? Except Maha. Again, I'm sorry, I'm not able to read chats because I'm writing on the blackboard. Maha, what's the problem?
No, I suddenly lost the connection and now I can.
But this is your computer problem, right?
Yeah, it happened also this morning.
But you have both PC and laptop, right? Try to turn on both.
Yeah, it's same. Yeah, okay.
So maybe as an exception, you can go to somebody else's room, to Lian, to Pooja, because two persons can, to Julia, who can see the screen.
Okay. Yes, okay. I will try.
Okay? I continue.
Can you increase on the signal direction?
Okay, I will write with the bigger letters. So, as I said, I'm going to define longitudinal response, which is parallel to Q. Because the transverse part of the electric field and electric field E and electric field D, which is orthogonal to vector Q, will not be captured by this equation. I need to do something else in order to discuss transverse response. But for all purposes of today and tomorrow lecture, I am dealing with longitudinal and longitudinal response. So the equations which I wrote, the Maxwell equation, read I, Q, E parallel, and without losing generality, I will denote E parallel and D parallel as E. Is equal to, this is function of Q omega, is equal to 4 pi E rho total as a function of Q omega. So I did Fourier transform of both right hand side and left hand side. I, Q, D, Q omega is equal to 4 pi E rho external Q omega. Okay? Then I define a function which I will denote epsilon Q omega, which is ratio of rho external Q omega and rho total Q omega. So this is a definition. This is the dielectric function. The logic is like that. I insert some extra charges into the system, and I have induced charge, and external charge plus induced charge are equal to total charge. So rho total is equal to rho external plus rho induced. Therefore, rho external is equal to rho total minus rho induced. And therefore, I will continue this line as 1 minus rho induced as a Q omega divided by rho total Q omega. This is what I'm going to compute now, and although, as I said, that on Wednesday we will have a discussion and we will see that most of these phenomena are classical, in particular phenomena associated with the fluctuations of the density of charge, I will use quantum mechanical derivation. So I will start with the Schrödinger equation and I proceed with the time-dependent perturbation theory, which you studied in the course of advanced quantum mechanics, in order to derive this quantity. And you know that in quantum mechanics, it's possible to take semi-classical limit, it's possible to take h bar and send it to 0, and then we will see each equations contain h bar and which equations do not contain h bar. So it's not a crime to do quantum mechanical calculations, because by doing quantum mechanical calculations I can also take properly classical limit, but not other way around. If I have a classical calculation, there is no way to go to the quantum limit. Okay? So, is it clear what I am going to compute? Okay. I will probably rewrite this equation on the top. So epsilon q omega is equal to 1 minus rho induced divided by rho total.
Professor?
Yes?
Just a question, but not really on the topic. Do you have some kind of handout that we can read?
Something what?
Something like a handout or lecture notes, like quantum mechanics lecture.
Well, as I said, the lectures are online. Writing lecture note is actually a lot of work. We are working on this direction, because if the situation with Corona will persist, we'll definitely need to produce some lecture notes sooner or later. But for the moment, I recommend you literature. There is no unique book which I'm taking for giving my lecture, but some derivations are sort of unique. They are not written in any textbook. I would rather recommend you to re-watch the videos. There are no lecture notes so far. Sorry. Okay, so let me remind you something from quantum mechanics, which you already learned in advanced quantum mechanics course, but I need it for consistency of my derivations. So let's define the density of operators. We have a discrete charges placed somewhere in the metal. I'm not assuming that we have a regular crystalline lattice. It doesn't matter for my derivation. We can equally have irregular system of charges like electron gas or whatever. So the density operator ρ, which depends on the coordinate, I assume the charges, well, in principle, I can also consider time dependent of charges, like in a gas, charges can move. So this is sum over A positions of your charges, and you have a delta function R minus RA. So this is operator in the first quantized language. I'm going to write it in the second quantized language. So the operator ρ after second quantization is equal to sum over k prime sigma. We have a k prime, a delta k sigma, a k prime sigma, where the matrix element a k prime, according to the rules of second quantization, this is integral over dRa. I have a wave function which I took from my first quantization. Wave function k Ra, delta function R minus Ra, psi k prime Ra. Of course, if I consider the wave functions as a solution of time-dependent Schrödinger equation, this is what I'm going to do. I will add the time, which will sit in the definition of the wave functions. Okay? So, since it's a delta function, I have a point-like impurities. I can easily evaluate this integral. This is then psi dagger k r psi k prime r. Now I'm going to compute the expectation value of this operator. Therefore, I need to take an average of this operator ρ, the density operator, with respect to the ground state. I'm dealing with the ground state now. So this is quantum mechanical average. I will denote this ρ. Now I don't put hat. As a function of R, now I put T. This is averaging over ground state. Operator ρ, R, T. So this is many-body quantum mechanical averaging with respect to ground state. So basically, what I need to do is to take averaging of the product A k dagger, A k prime, averaging. You see, we have a vacuum to the left, we have a vacuum to the right. We create state with a momentum k prime. We annihilate the state with the momentum k prime, and we create state with the momentum k. we know, and you know it from the second quantization, that this average is equal to 0 except that k is equal to k prime. Therefore, this is delta k prime, because if k prime and k are different, you are acting by k prime to the left side, you are acting by k to the right side, and you get two orthogonal states. And then we have a sigma, and here we have k sigma, which is a Fermi distribution function. I denoted it like that. However, for the purposes of my today's lecture, I will use shorthand notations. Chi sigma is equal to nk sigma. So this is a Fermi distribution function. I'm not going to talk to Bose particles today. This is the definition. So therefore, this expectation value of a density is, I plug in my operator. So this is A. Sorry, I already did that. I plug in A from here, and I use the fact that the average of A dagger A is proportional to delta symbol. So this is K sigma. I have a psi modulus RT square times nk sigma. So this is the expectation value of the density operator. Now, as I said, that it doesn't matter whether I'm on lattice or not. From now on, I will consider free gas of electrons. So since electrons are free, as a zero approximation, I will consider the free gas of electrons. However, in reality, the system of electrons is subject of Coulomb interaction. So what I'm going to do is to consider Coulomb interaction, long-range interaction between electrons by perturbation theory. So I need to develop time-dependent perturbation theory considering interaction as a perturbation. So as non-perturbed zero-order wave function, I'm going to use free electron gas. So this is K as a function of RT, and you know that the psi node, and you know that the wave functions of free electrons are just plane waves. So this is what I'm writing down. So I will denote omega as the volume of the system, because letter V will be assigned for the interaction. So this is the volume. And I have a plane wave, I k r minus I epsilon k t divided by h bar. So these are plane waves. And we know that plane waves form a complete basis of the wave functions. Therefore, I can write my wave function psi rt, which with index k, which I need to find, being expanded on the full orthogonal basis with the sum coefficients. So this is the sum of the k prime, c k prime, psi k prime, 0 r t. And this coefficient also depends on t. In principle. So this is expansion of my unknown wave function in terms of the full, complete orthogonal basis of the functions, which zero-order wave functions, which are plane waves. What I'm going to do, as I said, I'm going to insert charges into my system, compute response to these external charges using perturbation theory, and then compute the dielectric function. Is my logic clear? Maha, are you now with Julia? Can you see what I'm writing?
No, it's yes, it's okay now. I'm in my room. It's okay.
Okay.
I'm using the computer.
Okay.
Professor,
Yes.
what did you write for the coefficient of the sine
These are unknown coefficients which I am going to find using perturbation theory. This is what I am going to be occupied for next 15 minutes.
But I cannot see the notation, the CK something.
So here we have C with a sub-index K prime as a function of time times psi K R T is equal to sum over K prime C K prime T times psi node K prime R T. Okay? So, the goal for next 15 minutes is to find the wave functions, namely coefficient Ck prime, using time-dependent perturbation theory. And this is what I suppose you know how to do. Nevertheless, I will do it from very beginning to very end, and this would be nice repetition, nice exercise for your advanced quantum mechanics. So, the Schrödinger equation, my wave function psi, satisfies the Schrödinger equation time-dependent. Schrödinger equation psi R T is equal to H psi R T. Well, we can put index K, we can skip index K, doesn't matter. I'm talking about this function. My Hamiltonian consists of H node, which is kinetic energy, which is K squared over 2m, H squared K squared over 2m, plus some interaction. So this is Coulomb interaction. My function psi node, I H bar d over dt psi node R T satisfies the Schrödinger equation with H node. By the definition, as I said, I defined my wave function plane wave, just free motion of electron, kinetic energy only. So now I'm going to plug in this wave function into the full many-body Schrödinger equation and see what kind of simplification appears. I'm writing I H bar d over dt sum over k prime c k prime t psi k prime 0 r t. So this is the left-hand side of this equation. And let me massage it a little bit. I have a time derivative. So therefore, since both terms depend on time, and I have a product, I need to differentiate each term. So first of all, first term is I H bar sum over k prime d c k prime t over d t times psi node k prime r t plus the second term sum over k prime c k prime t times I H bar d psi node k prime over dt. Let me put k just for your convenience. Okay, so the second term can be simplified using the second Schrödinger equation. Therefore, I continue it here, keeping the first term intact. This is sum over k prime d ck prime over dt psi k prime node r t. And the second term plus, since the right hand side gives me h node psi node, I can write it as h node sum over k prime c k prime psi k prime node r t. This is all about the left hand side of the equation. Now, I will write this as left. Now I write what is on the right hand side. This is h node plus v times sum over k prime c k prime psi k prime node over r t. So you see that I have a term with h node which cancels out. The same term exists in the left hand side and in the right hand side. As a result, I have a Schrödinger equation I h bar d sum over k prime d c k prime over d t is equal to psi node k prime r t is equal to v times sum over k prime c k prime node c k prime psi k prime node r t. This is exact Schrödinger equation. I did not yet make any approximation. Is it clear what I did? I will tell you when approximations start. So this equation is still requiring some massage, and what I will do, I will multiply the right hand side and left hand side of this equation by psi node star. So what I will do, I will multiply the left hand side to the function psi k double prime node r t and proceed with integration. And I will do the same with the left hand side. So I will multiply psi k double prime star node, this is star r t. And I use the fact that I have an orthogonal basis of these functions. Therefore, the integral over these two functions, this and this, will give me a delta function k prime, k double prime, and therefore I have I h bar sum over k prime now is gone, d c k double prime over dt is equal to, in the right hand side I will have a matrix element. I will have an integral over dr. Remember that v depends on r and t. This is my interaction. I have integral over dr psi k double prime node star r t v r t times psi k prime node r t. And this I denote as v k double prime k prime. So this is a matrix element. So in the right hand side, I have a sum over k prime, v k double prime k prime times c k prime. This is a Schrödinger equation written in the moment of space. It is still exact. I did not yet make any approximation. However, now I'm going to start with approximations. Okay? You remember that I'm doing the perturbation theory. Therefore, in the spirit of perturbation theory, I say that in this sum, I have a state with k prime equal to k. And for state with a k prime equal to k, I use psi node. And all k not equal to k prime not equal to k, will provide me correction, and this correction depends on the interaction. So therefore, I write that ck is equal to 1, but ck prime not equal to k can be obtained from this equation. So ck double prime not equal to k, I have equation that I h bar d c k double prime over dt. But here, in the spirit of perturbation theory, I will plug in the only coefficient. So, since I'm doing perturbation, v is my small parameter. We discuss small parameter at the end of calculations, real small parameter in the system. So in this sum, I can take only one term with a k prime equal to k. So this is v k double prime k is a function of t. Because, as I said, what I did, I said that coefficients for ck is equal to 1. If k double prime is not equal to t, I will get first correction proportional to v, but in order to elaborate this correction, I keep here only term iteratively, where k prime is equal to k is equal to 1. Okay? So, this is approximation. However, from this approximation, I can write that ck double prime not equal to k is equal to minus I divided by h bar, integral from minus infinity to t, v k double prime k, function over t prime, d t prime. Okay? Now, I introduce, in the spirit of what I discussed in the very beginning, I introduce some external charges into the system and compute response to these external charges using perturbation theory. So, I'm going to use monochromatic wave. So, I will assume that my external charges, potential, so now I'm talking about V, but first I say that the external potential is equal to some V tilde Q times I Q R minus I omega T. I use monochromatic wave plus V Q tilde star e to the power minus I Q R plus I omega T. But I need to have a total potential. Therefore, I'm saying that if I insert charges into the system with some effective external potential, the total potential will follow the same form. Therefore, V, which is a total potential, which I'm going to find at the end of the derivation, is equal to VQ, some another matrix element, not coinciding with this, times IUR minus I omega T plus VQ star e to the power minus IQR plus I omega T. For what I'm doing with this perturbation theory, I will completely ignore the fluctuations of density at this very moment. Therefore, what I'm doing is called random phase approximation. And when we proceed with the calculations. We will discuss when this random phase approximation is applicable. Just to anticipate it, I need to tell that it is applicable at the large density of electrons. We know that metals are good metals when the density of carriers is high. So the Coulomb potential can be treated by the perturbation theory when the density of carriers is very high. Why? Coulomb potential behaves as E squared over R. We need to treat potential energy, this is the potential energy of our many-body system, being small compared to kinetic energy. So let me replace R by some mean distance between particles, and therefore we need to request that it is smaller than kinetic energy, and kinetic energy is h squared over 2m r bar squared. So in this inequality I can draw factor of 2, it doesn't matter. Therefore, if I rewrite this inequality, then I will write that R bar should be much smaller compared to the H bar over ME squared. From your quantum mechanics, you immediately recognize that H bar over ME squared is nothing but Bohr radius. So I'm saying that mean distance between particles, between electrons, should be much smaller compared to Bohr radius. But the mean distance, R bar, this is 1 over Fermi momentum, because we remember that Fermi momentum is proportional to the density to the power 1/3. Therefore, density is number of particles per volume, so the mean distance is inverse per Fermi. So therefore, the criterion of applicability of what I'm doing is Pf times Bohr radius is much larger than 1. I have high density of electrons. And this sounds very unusual, because next week we start with the Bose gas, and we will see that the low density limit corresponds to the weak interaction in Bose gas. So what is the puzzle? The puzzle is that we are dealing with a long-range interaction. Coulomb interaction is a long-range interaction. For Bose gas, for uncharged particles, and if we have an electron with some additional short-range interaction, we will also proceed with a different way. We start to compare potential energy and kinetic energy, and we will see that weakly interacting gas corresponding to low density. The gas parameter should be small. However, the long-range interaction changed this criteria. So the message is that the metals are good metals at very high density of carriers, and if it is so, we are allowed to proceed with perturbation theory, treating the interaction between particles as small effect. Good. So, now,
Professor,
Yes.
I have a question.
yes,
So, this high density limit, this is the same saying that we're in the regime of Fermi liquid, right? Fermi liquid theory.
yes, yes. To be, maybe I come to this point on Wednesday. There is some parameter which is called RS, which actually controls the high density limit. You see that I'm comparing everything with the Bohr radius. For true, high density, this RS should be very small. But in real metals, this RS, if you plug in realistic parameters for typical metals like sodium, aluminum, you will get that RS in the best situation is of the order of 1. However, if you increase this RS, what then happens? Then the system crystallizes in so-called Wigner crystallization, and for three-dimensional situation, crystallization appears at RS being 37. RS is dimensional parameter. So you see that as long as your RS is not much smaller than 1, but of the order of 1, you have a metal. If RS becomes larger, then you have a transition at low density. The Coulomb interaction is the main interaction in the system. Kinetic energy is small compared to the potential energy, so one can treat kinetic energy by perturbation, and system is crystallizing, actually forming some crystal, which at the same time is perfect antiferromagnet. But I'm not going to discuss that. I'm even not going to define properly this RS. I'm saying that my mean distance between particles is much smaller compared to Bohr radius. Yeah. And Bohr radius, you know, is half an angstrom for Bohr, for the hydrogen atom. This is really very high density. Typically in the crystals, the Fermi momentum is of the order of lattice spacing. The lattice spacing of the order of few angstrom, and this is what I'm saying. That typical situation, we never have much larger. We have of the order of 1. But the physics of crystallization appears at much, much larger distances.
Thanks.
Okay. So, now, I will take this potential and plug it in here. Because I'm going to compute these coefficients, compute wave functions, and so on and so forth. And today, by doing these calculations, we have several important physical aspects which we need to discuss. Which actually makes a difference between pure mathematics and physics of what we are discussing. So, I plug in this wave function to matrix element which I just eliminated. This is minus A divided by h bar, 1 over volume, because I have a product of two wave functions. And here, I have integral, this choke, stereo. So, first of all, I have a dr e to the power psi naught star with a subindex k double prime minus I k double prime r plus I epsilon k double prime t over h bar. This is a wave function psi naught k double prime times my potential Vq e to the power I ur minus I omega t plus Vq star I minus I qr plus I omega t times psi psi k node, which is 1 over square root of volume. I already put it in front. E to the power I k r minus I epsilon k t divided by h bar. So I put everything together. So this is related to psi node star k double prime. This is related to psi k node. So, integral over dr. I have r here, I have r here, and here, and here. But these are two terms. When I take integral of exponent, it gives me the Kronecker symbol. So, the integral e to the power I q minus k double prime plus k prime r over dr is equal to volume times delta function k double prime k plus q. I will write it down again, don't worry. So, using this, I sort out and there is an integral from minus infinity to t d t prime. Okay? So the integral over r can be evaluated with the help of this. Now we have integral over dt prime. So it's a t prime, it's a t prime, it's a t prime, and it's a t prime here. I have an integral over dt over periodic function, because everything what I have here are sines and cosines, are exponent. So the integral at the lower limit at time equal to minus infinity is badly defined. So I need to regularize my integral at the very past. So I'm saying that I have so-called adiabatically switching on the interaction. So if it's my time error, so it's time. Somewhere here I have minus infinity, here I have time moment which I'm going to discuss. I'm saying that my interaction is adiabatically switched off at time equal to infinity. Therefore, in order to guarantee that, I will multiply my integral to delta t prime. Then this exponent will guarantee that my integral is convergent at t prime equal to minus infinity. And then, at the end of the calculations, I will put delta goes to 0. So to say, I'm taking limit, delta goes to 0. So I will regularize my integral additionally in order to provide convergence at the very past. And this is a physical assumption that at the very past, my particles didn't interact at all. So delta t is I multiplied minus I t prime. So in a sense, I need to add to my frequency either I delta or minus I delta, which means we are dealing with so-called retarded or advanced response. Here we are dealing with causal response, so it contains retarded and advanced part. So retarded means that our future depends only on past. Advanced means our past depends only on future, so to say. However, having done that, I can write down the integral. So the integral of exponent will of course be 1 over argument multiplied by exponent. In the lower limit, the integral is equal to 0, and I'm now writing the result in the upper limit. Okay? So,
Professor. Hello?
yes, yes, yes.
I don't understand why you suddenly insert the exponent to the delta t and
Because as I said, look, I'm computing integral over dt prime from minus infinity to t, and here I have some combination of exponents, I, b, t prime. What this integral is equal to? This integral is equal to 1 over ib, exponent I, b, t prime in the limit of minus infinity to t. But how I define exponent to the power I, b, t prime at the lower limit, minus infinity? It's better defined quantity because I have a oscillating function. However, if I add plus delta t, then I have delta t and plus delta here. Now I can take a limit at minus infinity, because at minus infinity this term is negative, therefore exponent is equal to 0. On the upper limit it gives me b t prime, and then I take limit delta equal to 0. So I'm regularizing and redefining and regularizing my expression at time equal to minus infinity. Okay? Otherwise, I have sort of ill-defined quantity. And this is very physical, because I'm saying that at the beginning of everything, beginning of universe, my particles didn't interact. And then the interaction was adiabatically turned on, and this is adiabatically switching on the interaction. Okay, C k double prime not equal to k is equal to. So now I will put h bar equal to 1 from now on. Otherwise, I have two long equations. So this is equal to minus fraction epsilon k double prime minus omega minus epsilon k prime, sorry, epsilon k, because I have a k, minus I delta times v q e to the power I epsilon k double prime minus epsilon k minus omega t. This is the first term. Plus minus 1 divided by epsilon k double prime plus omega minus epsilon k minus I delta v q star e to the power I epsilon k double prime minus epsilon k plus omega t. So I just computed the integral which was written on the blackboard. Now I can plug it in here, and I'm writing that psi k r t is equal to, in the sum I have a term k prime equal to k. For this, ck is equal to 1. Therefore, I have a psi k node r t plus sum of k prime not equal to K. So this is then minus, because I have minus here, minus sum over K prime, not equal to K. And this is 1 over epsilon K prime, because now I put K double prime equal to K prime, K prime minus K minus omega minus I delta. Here I have the Q. And what I forgot to put here is this delta symbol, which I put here. So this is delta symbol, K double prime, K plus Q. And here I have a delta symbol over K double prime equal to K minus Q. This appeared from the integration over R. So dq, delta symbol K prime, K plus Q, e to the power I epsilon K prime minus epsilon K minus omega t, plus the same term where I have the second exponent. Plus VQ star delta K prime K minus Q e to the power I epsilon K prime minus epsilon K plus omega t divided by epsilon K prime minus epsilon K minus plus omega plus I delta. And of course here I have upside node K prime RT, and here I have upside node K prime RT. Okay? Bracket is closed. So now I'm ready to take sum over K prime, because I have a delta symbol which tells me that in the first term K prime is equal to K plus Q, in the second term K prime is equal to K minus Q. So psi K R T is equal to psi K node minus V Q e to the power I epsilon K plus Q minus epsilon K minus omega t divided by epsilon K plus Q minus epsilon K minus omega minus delta times psi K plus Q node R t minus V Q e to the power I epsilon K minus Q minus epsilon K plus omega divided by denominator, epsilon K minus Q minus epsilon K plus omega minus I delta psi K minus Q node R T. Good. So K plus Q, K minus Q. This blackboard is too small to write down. Let me write down explicitly the form of the wave function. So psi K is written here, node K plus Q R T is equal to 1 over square root of volume. And here I have exponent I K plus Q R minus I epsilon K plus Q T. H bar is equal to 1. Psi node K minus Q R T is equal to 1 over square root of volume e to the power I K minus Q R minus I epsilon K minus Q T. I need to plug in everything here, and as you see, I can factorize. So I will take out psi node everywhere, and I will write in the bracket all the rest terms. So I will continue. Sorry?
I just want to clarify something on the board. Look at the expression you wrote for psi k of r, the last term is equals psi naught k minus psi k. Or
this is k minus q.
No.
This is k minus q, and here it's k plus q.
Close. After that, the last expression I mean.
In last expression, k minus q,
No. Here, go back to the expression for psi k of r.
Yes.
And look at the last expression.
This one?
Yes.
So this is product. This is product.
That was what. Okay.
Yeah. This is a product. So this is then equal to psi k node. I put it out of the bracket, and here I have 1 minus VQ e to the power I minus I omega t plus IQR. This is IQR. Epsilon k plus q cancels out. Epsilon k is taken out of the bracket, divided by, actually I don't need this delta anymore, I can put it equal to 0. Epsilon k plus q minus epsilon k minus omega minus VQ star e to the power, here I have I omega t minus IQR divided by epsilon k minus q minus epsilon k plus omega. That's it. So, in the lowest order of perturbation, lowest order V, I wrote this expression. Now I'm ready to take psi modulus square. This is what I need for my density operator. Okay? Are you still with me? Where is this cleaning? Okay. Now I don't need this anymore. I didn't promise that there will be simple calculations, but we are learning a lot of physics with this. And I am almost done. So, I need to compute psi k r t modulus square. This is psi k star r t times psi k r t. So what I do, in order to compute psi k, I will complex conjugate this. Psi k is already written here. And then, by multiplying psi k star by psi k, I use the fact that psi k node star times psi k is equal to 1. And I only keep terms linear in their potential. So multiplying this bracket to complex conjugated gives me 1 minus. Now I collect terms in front of VQ e to the power I Q R minus I omega t. And there are two terms. One is epsilon k plus q minus epsilon k minus omega, and another one is epsilon k minus q minus epsilon k, sorry, it's k minus q of course. Sorry, no, it's correct. Epsilon, yeah, k plus omega. Then I have a term minus v q star e to the power minus I q r plus I omega t. And surprisingly, we have the very same term. 1 over epsilon k plus q minus epsilon k minus omega plus 1 over epsilon k minus q minus epsilon k plus omega. So this one is a density associated density in the system in the absence of interaction. So rho, I remind you that rho RT is equal to sum over k n k sigma times psi k r t modulus square. Okay. What I forgot to write down, that normalization of psi naught is 1 over volume. Yeah. So, I'm almost done. I keep my potential, which is good. So, from this, I can write down that my induced charge, rho induced, 1 is associated with a charge without interaction. My induced charge is equal to minus V total, because this is the same term. The bracket is the same at q omega divided by omega capital, and here I have sum over k sigma and k sigma, and this bracket epsilon k plus q minus epsilon k minus omega plus 1 over epsilon k minus q minus epsilon k plus omega. For those who know electrodynamics, understand that this is emission and absorption photon with a frequency of omega. I have induced charge, I need to divide it by total charge, and then I get the electric function. The rest is to write down what is the total as a function of q orbit. In order to do it, we go back to electrodynamics and write down Poisson equation. So Poisson equation tells us that V total is equal to charge times potential phi total. Divergence of E is equal to phi par rho total from the Maxwell equation. However, E is equal to minus gradient phi. If I plug in everything here, I have closed equation for phi, namely number of phi is equal to minus 4 pi rho total times charge of electron. So, and this is total. This is so-called Poisson equation. To solve this equation, we make a Fourier transform, which tells us that q squared 1 over omega q squared times phi is equal to 4 pi e times rho total. Therefore, V total, which is phi times e, is 4 pi e squared over q squared times volume times rho total. So now we closed completely our equation. I plug it in here, divide by rho total. So what I get is that my dielectric function E q omega is equal to 1 minus rho induced divided by rho total. So this is 1 plus 4 pi e squared over q squared. Volume cancels out, and here I have sum over k sigma. In this term, let me denote k plus q is equal to some k prime. Therefore, k is equal to k prime minus q. And since k or k prime are my silent indexes, then k plus q is equal to k is equal to k minus q. So I have term similar to this one. I have epsilon k minus q minus epsilon k plus omega, and here I have nk minus nk minus q sigma sigma. Oof! This is my dielectric function, which I'm going to compute on Wednesday for parabolic dispersion of the spectrum. I'm going to compute it at 0 temperatures, and we will discuss properties. This is a function of q and omega. Sometimes this sum, so this is bare Coulomb interaction. You recognize that this is Fourier transform over e squared over r for three-dimensional situation. Sometimes people define quantity p q omega, which is minus sum over k sigma, n k sigma minus n k minus q sigma, and here there is a denominator, epsilon k minus q minus epsilon k plus omega. For those who are familiar with Kramers-Kronig relations, which is actually Cauchy theorem in the theory of complex variable, we can be back to retarded or advanced sector, because this is a function of a complex variable. This is analytic function, which is analytic in the upper half plane of omega. Therefore, it has real time and imaginary time. Imaginary time will be responsible for damping of your quasi-particles associated with the fluctuation of density. I'm preparing what we are going to discuss next time. And this dielectric function is actually important because the total interaction, q omega, or effective, is just equal to V node. This is V node divided by 1 minus P V node. This function P is called polarizability or polarization operator. And if we look at this expression, so this is nothing but V node divided by epsilon. So V node divided by epsilon Q omega. U. If you look at this, so this result actually resembles summation of geometric progression. We can expand our denominator and write it as an infinite series. So V effective Q omega is equal to V node plus V node P V node plus V node P V node P V node plus and so on and so forth. So this form, or this form, is called in the literature as random phase approximation. Random phase approximation. And it actually corresponds to ignorance of the fluctuations. This random phase approximation is valid when the perturbation theory is valid, namely for the large density of your charged particles. There are many body tools for computing this polarizability. For example, this result, which I spent 1.5 hours today to derive, can be derived in 15 minutes using diagrammatic technique. So therefore, I encourage you to learn some tools. But in order to present you derivation with the help of green functions or Feynman diagrammatic technique, I need at least 3 or 4 lectures in order to give you a basis of many-body perturbation theory, not related to the way I derived it today using time-dependent Schrödinger equation. So, investing your time in learning some techniques, analytical, numerical techniques, is a very good idea, because you can invest time in learning, but then you save time in the derivations. One can elaborate corrections to this random phase approximation, and this again is controllable by parameter inverse to this. This is going to be small parameter of perturbation theory. So this is what we did today, and on Wednesday, as I said, I will be spending the whole lecture by first of all computing this dielectric function in a static limit, namely at omega equal to 0. Then we will see temperature equal to 0. Temperature doesn't play any important role anymore. Then we will see that it results in screening of a Coulomb interaction. So the Coulomb interaction from the long range becomes a short range. You cover potential. Then we discuss this function in the limit of small frequency. We will see that the poles of the effective potential, which corresponds to 0 of the dielectric function, will define as branch of the excitations. Excitations in this fermionic system are bosonic. Like phonons are excitations associated with the fluctuations of the density. You don't need crystal to have a phonons. We are speaking in the room. There are density waves of the air. This is the sound, and these are phonons. The excitations in the system of charged particles are called plasmons. They are not sound-like. In 3 dimensions they have a gap, and there is reason for that. We have a long-range interaction. And last but not least, we discuss Friedel oscillations. So what happens if you introduce charge impurity into your metals, and discuss what is called RKTY interaction, which are pretty the same, 2 sides of the same coin. So these are plans for Wednesday. Any questions so far? I understand this is tough, and especially it's tough doing online, and it's tough to do it on very small blackboard. However, well, I think I managed to do it, but you need to digest it. So I'm not requesting that you understand everything from very beginning. You need to go through, and you need to think about it, and you need to digest the result. Okay. Maybe I will ask Andrei to rediscuss some parts of it if you need during tutorial. As I said, Wednesday it will be just pure mathematics. We will be computing this integral with the Fermi distribution functions. We will see some logarithmic singularity and so on and so forth. But this will be pure mathematics, out of which we will draw many interesting physical conclusions, and in particular I will explain you why metals are shiny. Okay, if nothing to ask today, I'm just wondering why there are 17 persons. I would expect that we should have 15 or something like that. Because Maha is connected twice, then there are 2 rooms. Okay, then we are done for today. Thank you very much. That's it. Bye.